Hello, everyone. Today, we're going to start our discussion about risk assessment. This is a two-lecture series in which we first talk about how to model and quantify risk and learn some of the definitions that are used in the risk assessment domain. And hopefully, in the next lecture, we'll talk about a framework for risk management. How do we try to minimize risk? Um, Risk is actually a very confusing word because when you talk about risk or something which is high risk or low risk, different things come to people's minds. Some think of it as chance, likelihood, probability, possibility. Some may think of it as a hazard, as a threat, as a danger. In reality, none of those terms actually provide an accurate definition for risk, and defining what risk is not an easy task. In our approach, we try to model risk by answering the following three important questions. First, what can go wrong? What is the likelihood of that happening? And what are the consequences? This is in lines with the expected utility theory that was developed by the 18th century Swiss mathematician Daniel Bernoulli. He defined risk as consequence times the probability of that consequence. And in case you have multiple events or consequences that are independent of one another, he defined the overall risk as the sum of all the probabilities times the corresponding consequences. The one thing you notice in this equation is that since probability is a dimensionless value, the units of risk are actually the same as the units of consequence. So if the consequence in your analysis is financial losses, the risk is going to be in dollar value as well. For human attacks, we try to model risk differently. So instead of looking at probability consequence, we kind of break it down into what is known as a threat asset pair. And for a particular asset, we define risk to that asset I as a multiplication of the threat that is, threatening that asset, the vulnerability of that asset, and then the consequence of if that threat to that asset is materialized. And the threat is further divided into intent and capability. Intent, as the name says it, is try to quantify how willing and how willing the attacker is, how much tendency the attacker has to mount that attack. Capability talks about the ability of the attacker to mount a successful attack. Um, this model, however, is being criticized by some people because some believe that the threat is actually not an independent variable. And they argue that the threat to an asset is, in fact, a function of its vulnerability, meaning that if an asset is vulnerable, more vulnerable, the attacker is going to be more willing to mount an attack. So some people consider it that way, but of course, if we consider threat to be a function of vulnerability, would make the system more complicated. We'll talk more about this later when we come back to our discussion on terrorist attacks and how we can model it, how we can mitigate it. Risk has become a very, very important part of our modern engineering systems, and there's a lot of reasons for it. Our modern systems are becoming more complex and consist of subsystems that are highly interdependent and coupled. And if one thing goes wrong with one part of the system, every other subsystem might be affected by it. Cost limitations sometimes force us to postpone, maintenance schedules or, required upgrades, which would make the system more vulnerable to different types of threats. We have more competition, which would open the door to, industrial sabotage or, industrial cyber intrusion, cyber attacks. Natural disasters, of course, are a very significant part of our modern life and are threatening all critical infrastructure, including the power system. When it comes to transportation systems, things are moving at higher speeds, which would make it a, higher risk compared to vehicles or airplanes or systems that move at lower speeds. We of course have terrorism, which is human-based attacks. We have more automated solutions that perhaps bypass the sanity check of a human operator, which could in certain situations make it more vulnerable to different types of unwanted events. Sometimes when you have a workforce which is multicultural, there may exist cultural barriers or communication barriers that could lead to misunderstandings that could threaten the operation of a system. And of course, again, because of cost and budget limitations, systems are operating at either at rated levels or very close to those, meaning that we have smaller margins for error. In power systems, for example, a very simple outage of one line or transformer or a generator could in fact trigger a cascading failure because we do not have enough safety margin in terms of reserve capacity or, for example, additional capacity in our overhead lines. All right, let's start our discussion on risk assessments by going through some basic definitions. The first one is hazard. Hazard is basically a source of danger that could cause harm to an asset. So it's a source of danger that is kind of over the head of your asset. But in order for that hazard to become a hazardous event, you need a triggering event. A triggering event, for example, this wire tearing up, that would turn that hazard into a hazardous event, which when it's, when it occurs, it leads to a consequence. So we have a hazard, which could become a hazardous event, and if it does happen, would lead to consequences. Next, we have the notion of accidents. Accidents is an event or a sequence of events that is sudden, unwanted, and unplanned. We can have a single accident, or we can have an accident scenario in which you would have an initiating event, which could change a hazard into a hazardous event. And this hazardous event could lead to other events, which could eventually terminate at an end event. This collectively would be an accident scenario. Related to the definition of that term accident, we also have incident and near accident. Incident is again an event that is unplanned and unforeseen, but it may or may not result in harm to assets. And near accident, again, is an event which is unplanned and unforeseen, which could have resulted in harm to assets, but it didn't. Now, accidents can be categorized into three groups. Category one consists of accidents that are high frequency, low impact. Examples of these would be traffic accidents or minor occupational accidents in industrial settings, things that happen typically on a regular basis, but they do not lead to catastrophic consequences. Category two is relatively infrequent compared to category one, but has a much more severe consequence. Think of it as air accidents or railway accidents or major industrial accidents. Category three, on the other hand, is known as high impact, low frequency. Often it's known as the acronym of high impact, low frequency, HILF. These are events that are very, very rare, but if they do happen, they have catastrophic consequences. An example of that would be a nuclear accident. The next important terminology is a barrier. A barrier is a system or a feature that tries to sit between the hazard and the asset to protect your asset. It also comes with different names. Some refer to it as countermeasures, safety functions, defense measures, line of defense, protection measures, safeguard. All of them mean the same thing. And the function of this barrier is either to prevent the undesired event or to control the undesired event. So if it does happen, try to contain the energy of that undesired event, or to mitigate its impact on the assets. So you can either have a barrier that tries to kind of prevent this hazard uh, from becoming a hazardous event, or it could try to, contain some of the unwanted consequences so that not all of it um, reaches the asset, or it may try to just protect the asset. So these are the different functions that the barrier can have. When we talk about barriers, there are so many different ways you can design a barrier. You can design a barrier which is merely providing understanding and awareness. So just educating people about the local hazards and what they should do should one happen. It could be a barrier in the form of guidelines and guidance. So how should you operate this machine or this system safely? A barrier could be an alarm. It could be a warning system that notifies people that a danger is about to happen and is imminent. A barrier could be a system that, if it identifies a off normal situation, tries to bring the system back to normal mode. A barrier could be literally a safety barrier between the hazard and the potential losses, meaning that try to minimize the amount of losses that could happen if that hazard turns into a hazardous event. It could also try to contain and eliminate hazards. This is something that is used a lot in, for example, nuclear power plants. There are barriers in place that make sure that if the unwanted event happens and there is a nuclear incident, the amount of radiation that reaches the outside world is contained as much as possible. If none of these work, a barrier could be basically providing a escape route or a rescue route for people who are affected by that hazard. So when you think about barriers, do not think necessarily that it's a physical system. It could be any of these things that would try to minimize the risk. And again, notice that we define risk as the probability of something happening times its consequence. So you could be trying to minimize the consequence or minimize the probability of that event happening. There are other ways in which we can classify barriers. One is to look at it in terms of proactive versus reactive. Proactive barriers, also known as preventative barriers or control barriers, they try to reduce the frequency of the unwanted event happening. Reactive, on the other hand, does not concern the frequency. Instead, it tries to reduce the consequence of the event. These are also known as mitigation barriers. Barriers can also be full versus partial. Full means that it's completely protecting your asset. Partial means that it provides some protection, but it's not a complete protection. An example of a partial barrier, for example, is an alarm system. An alarm system, if it functions properly, it will notify people about an imminent threat, and hopefully people can evacuate as quickly as possible, minimizing the consequences, but it cannot fully protect people. And they can also be classified as active versus passive. Active barriers are barriers that depend on something to be activated, either a human operator, a control system, or some sort of an energy resource. For example, think of an airbag. An airbag on its own does not activate, but when there is collision, the force of the collision causes the airbag to be activated. So that outside source causes it to be activated. Passive barriers, on the other hand, are kind of integrated into the design of the system, and they're always there. They don't need an external resource or a system or an operator to activate it. Examples, think of, safety shields that people wear in certain industrial settings. So that's always there. That is always trying to protect the asset, or the mid-road barriers in a roadway. Again, it's always there and it's always protecting vehicles, not waiting for an accident to happen. Another way to classify barriers is to look at it in terms of material barriers, functional barriers, symbolic barriers, or immaterial barriers. Material barriers are physical barriers, mid-road barriers, fences, guardrails, protective clothing. These are material barriers. Functional are barriers that provide certain functionality. For example, a safety lock, a password, an entry code. Symbolic barriers, these are barriers that require some sort of interpretation, and they try to protect the asset that way. For example, traffic signals, road signs, safety instructions, these are all symbolic barriers. Immaterial barriers are barriers that are not physically present. You can think of it as guidelines. You can think of it as laws that try to ensure safety for everyone. You can think of it as trainings for operators or monitoring systems, things like that. Now, let's think about this a little bit. For the specific example of driving a vehicle, what kind of preventive and reactive barriers can you think of? You can pause the video at this point, think a little bit about this, and when you're ready, you can hit play. So assuming you thought about this, you probably came up with a lot of the examples. Preventive barriers could be seat belts, headrests, the airbag system. These are some examples of preventive barriers. Reactive barriers that try to limit the consequence of undesired events. You can think of it as, for example, the ABS, the anti-lock braking system. You can think of it as the speed limits that we have on roads, or speed control, or traffic signals. So these are examples of reactive barriers. Okay, moving on in our review of some definitions, we come to vulnerability and resilience. Vulnerability is referring to the inability of an object to resist the impacts of a hazardous event and to restore to its original state. Opposite of that would be resilience. Resilience is the ability of the system to accommodate an external event, a hazardous event, without catastrophic failure, to kind of absorb the shocks and go back to either the original state or another safe state. Resilience is actually broader than robustness, because robustness only talks about being able to absorb the shock and withstand damage, but does not talk about adaptation to the new situation. Resilience, on the other hand, says, I am able to absorb a shock, reduce the consequences, and adapt myself into the new situation, go into a new operating mode. Okay, let's go back to risk again. So risk, as I mentioned earlier, is looking into three things. What can go wrong? What is the likelihood of that happening? And what are the consequences? So let's answer the first question. What can go wrong? As we saw, in every system, you're going to have different hazards. These hazards, if an initiating event takes place, might turn into a hazardous event, in which case you have lost the control of the hazard, and either directly or through some accident scenario might lead to an end event. This end event is going to have certain consequences. So the first thing that you have to do when you want to do risk analysis is you have to look at all the hazards that are threatening your system, look at all the initiating events that could turn those hazards into hazardous events, and then consider different accident scenarios that would lead to end consequences. The next thing is, what is the likelihood of that happening? So likelihood here, we look at it using the probability theory to each thing or event that can go wrong, we assign a probability between 0 and 1. So that event E is going to have a probability associated with it, the likelihood that it will occur. In order to assess and quantify the probability, there are different approaches. We can have a classical approach, a frequentist approach, or a Bayesian approach. In a classical approach, you're basically considering that there are a certain number of experiments. These experiments have some, finite number of outcomes, and each outcome is equally likely. You flip a coin, which is fair. There are two possible outcomes, head or tail, and the probability of each one would be 50%. So what you do is you look at the number of favorable outcomes divided by total number of possible outcomes, and that would be the probability of that event. Imagine we roll two dice and we want to know what the probability is for the sum of the two numbers to equal 9. So possible outcomes, obviously, is going to be 36 because you have 6 possibilities for the first dice and then 6 for the second one. And the favorable outcomes could be, for example, if they are 3 and 6, 4 and 5, 5 and 4, 6 and 3. So there are 4 favorable outcomes that would lead to some of those two numbers being equal to 9 divided by 36, which is the total number of possible outcomes, and that would be the probability of that event. In the frequentist approach, on the other hand, we consider that experiments are repeatable and can be repeated under the same conditions, but we do not consider that the outcomes are equally likely. So what we can do is, under the same conditions, we can repeat an experiment many, many times, look at the number of, favorable outcomes for event E divided by the total number of experiments. There are certain situations in which you cannot use classical approach. For example, imagine you're tossing a coin, which is not fair. If it's not fair, that means the probability of getting a head would be different from probability of getting a tail. So you're not going to be able to say, hey, I have two outcomes, head or tail, and they're equally likely. Instead, you're going to have to, toss this coin 500 times and see how many times you get a head. And then that would be the probability of getting head using a frequentist approach. The last approach is the Bayesian approach, in which we actually try to adjust the probability based on the information that we gain. So essentially, we try to adjust it based on the knowledge that is available to whoever is trying to analyze that situation. Example, you have a meeting, let's say tomorrow at 10 a.m. And you want to know, for example, the probability that it rains between 10 and 10:30. You look at historical data, you look at the skies, see if it's cloudy, if it's not, you look at the weather forecast, you use your personal intuition. Based on all this information, which is your personal knowledge, you say, hey, probability that it rains tomorrow is 50%, so I'm going to take my umbrella with me. That's your subjective way of assigning a degree of belief to that event that it may or may not rain. Now, in this approach, we often have two types of probability values. One is the prior probability and one is the posterior probability. Prior means that what is your belief as an analyst? What is your belief in occurrence of an event before you have any evidence from the outside world? You don't have any additional knowledge. Posterior, on the other hand, says you now have additional evidence, D1. So what is the probability of that event given you have additional evidence? And interestingly enough, if like a day later, an hour later, you have further evidence, D2, you can always adjust it. So this would be the first probability, which is probability of E given D1. And when you have both D1 and D2, you will adjust it based on this new information. And you get this new information and you can adjust the likelihood of an event taking place. So we talked about what can go wrong, what is the likelihood of that happening, and the third and last question that we have to answer is, what are the consequences? Now, in order to answer this, we have to address three things. First, what is it that you want to protect? That's your asset. What can happen to these assets? These are the consequences. And these things that might happen to the assets, how serious can it be? That would be severity. So you look at your asset, the consequence, and how severe these consequences are going to be. First, let's talk a little bit about an asset. Asset is something that you want to protect, something that has value to you. In different domains, it comes with different names. Some refer to it as target, vulnerable target, victim, recipient, receptor, and so on. If you're focusing on human victims, you can categorize your assets into first party, second party, third party, fourth party. First party are people who are directly involved in the operation of the system. Think the operators of a nuclear power plant. Second party system victims, these are people who are related to that system as users. So they have no really influence on how the system works or what it does, but they will be exposed to the risks. An example of this would be passengers on an airplane. So these are second party victims. Third party victims, these are essentially innocent bystanders, people who have nothing to do with that system who may fail, but if it does fail, they will be impacted. An example of this would be people who live in the neighborhood of a nuclear power plant. If there is a nuclear incident, they will be impacted by that. And then the fourth party victims, these are essentially future generations, people who are not born yet, but may be impacted by the negative consequences of a nuclear accident or, for example, climate change. So these are people who are considered to be the fourth party victims. So these are the assets. You identify the assets that you want to protect, and then you have to list the consequences. So what are the things that might happen? What are the impacts of that hazardous event? A lot of times, what we do is we look at it in terms of a consequence spectrum. So if you look back at what we talked about before, you have a hazard, a triggering event causes it to lead into a hazardous event, and the hazardous event would lead to different consequences, each one with its own probability. These consequences will only tell you what will happen, but how severe they are, in order to assess that, you have to look at severity. So how serious those consequences are. And in the same consequence spectrum, we can add functions for the losses, and that would make it a loss spectrum. So that hazardous event, there are multiple consequences, each one with its own probability. And notice that each one is going to have a loss associated with that. And now you can multiply the loss values by the corresponding probability, and that would be essentially the risk of consequence C1 or C2 or C3. And then when you add all those risks together, that would be the risk associated with this particular hazardous event. So to recap, if we want to define risk, we look at it as a triplet of event, frequency, consequence. What can go wrong? What is the likelihood of that happening? And what are the consequences if it does happen? You have to identify all the things that could go wrong, find the probabilities, look at the consequence of that event and its severity, and that will give you the full picture for risk. Let's close this chapter by looking at different ways that we can measure risk for various engineering systems. If you're looking at risk to people, you can overlay risk by the geographical map of the area. So you can calculate risk and say for all the people who are within this area, let's say this is a source of hazard. This is the amount of risk exposed to those individuals. Then this would be people outside that area, and this would be people outside again. Keep in mind that these risk contours do not consider things that people can do in order to escape an event. They're just saying that if you stay in that geographical location. This is the risk to which you will be exposed. We can also use a risk matrix. This is basically a way for us to show risk in a tabular fashion by looking at probability or frequency and consequence or severity. So in this row, we have, different probabilities. Events can be improbable, remote, possible, occasional, or fairly normal. And the consequences could be catastrophic, severe, major damage, damage, minor damage. And then, in a subjective fashion, you can allocate 1, 2, 3, 4, 5 to the probabilities and 1, 2, 3, 4, 5 to the consequences, add them together and get this table. So for example, the the lowest risk situation would be an improbable event that would cause minor damage if it does happen. And the highest risk situation would be if you have a fairly normal event that, if it does happen, would lead to catastrophic events. Um, but again, notice that this is a subjective way of quantifying things. There are some guidelines in order for you to kind of decide on some of those definitions in the previous slide. So for example, one example of how you can define frequency is provided here. So improbable, for example, less than 10 to the power of -5 events per year. And then you would increase it until fairly normal, which would be between 1 to 10 events per year. So that would be an event that is very, very rare. And this is an event that is, expected to occur very often. And then, other events would be in between. We can do the same thing for consequences. So one way to look at the severity of the consequence is to break down the impacts on people, on the environment, and on property. For example, catastrophic event, catastrophic consequence would have severity in terms of several fatalities on people, time of restitution for ecological resources being greater than 5 years, and total loss of the system, major damage outside system area. The other side of the spectrum, minor damage, for instance, can be defined as minor injury on people, minor damage on the environment, minor damage on property. Another example would be just to define the severity based on one description and not looking at different categories of people, environment, and property. For example, catastrophic would be an event that results in death or injuries and prevent performance of that system. Critical would be degrade the system beyond acceptable limits. If you degrade the system beyond the acceptable limits, but the system can be controlled somehow to be relatively acceptable, that would be major, not critical. And if an event does not degrade the system, then that would be minor. And then you can assign subjective, again, I emphasize subjective numbers, 1, 2, 3, 4 to those. One of the kind of better ways to do this is to use a definition based on ISO 17776, which looks at the severity of consequences quantified from 0 to 5. And again, here you can see that it's divides it based on people, assets, environment, and reputation. This reputation is put there to indicate the impact of an accident on the public relations of a company. So for example, if a utility cannot control its system and a major snowstorm leads to 10 days of everyone being without power, how much does it hit the reputation of that company or that utility? So this is where we're going to stop for this lecture. Again, my goal was to give you an overview of, what risk is, how we try to define it, and some of the basic terminology. Remember that we define risk using the utility theory by looking at probability of a consequence times the consequence. And in order to do that, we have to answer 3 questions. What can go wrong? So we have to list all the events that could be hazardous. What is the likelihood of that happening? So for each one, we have to identify what is the probability and what are the consequences in which we look at different things that might happen and the loss function or severity function associated with each one. These are the two references that I used for this lecture. The first book, especially the book by Rosand, The Risk Assessment. This is one of the best textbooks out there that looks into risk assessment. And I try to provide a very, very summarized version of some of the chapters of that book. But for those of you who want to learn more, want to see examples, there's a lot of examples and case studies in this book, and I recommend that you take a look.